So hopefully, I will indeed begin with the fiery diagram, because I think I'm a bit behind schedule. So we will start with a reminder of what we saw yesterday. That I still owe you like a correction of some computation, but yeah. So I think maybe next week I will give you the correction. So the reminder is about Penner's theorem, which is Ptolemy's identity in the hyperbolic plane, of course, appropriately stated. So the reminder is that, first of all, the definition of lambda length, or distance between two horocycles in the hyperbolic plane. So here what you are seeing is the Poincaré disk and its boundary at infinity, which is the unit circle. And first, one defines the signed distance between two horocycles as follows. Well, one has the two arbitrary horocycles, each one based at a point. Yeah. So each one based at a point, and each point, the two base points of the horocycles determines a unique shortest curve or geodesic on the hyperbolic plane, joining them even though they are points at infinity. First of all, and then this geodesic crosses each of the two horocycles I began with, and these points, let's denote them by Q1 and Q2. Yeah. So now we distinguish two cases. One where the two horocycles don't cross each other, and the other one where the two horocycles indeed intersect. In the first situation, when they don't cross, we define this sign epsilon to be plus, and if they cross, we define the sign to be minus. First thing, and second, we consider the hyperbolic distance between Q1 and Q2, which are the crossing points, or like the cutoff points provided by the horocycles. We take such hyperbolic distance, and then we take exponential of half this quantity. So you see, it's the exponent. The exponent is half the signed distance between Q1 and Q2. Yeah. And this exponential, which if you think about it, is like square root of exponential of epsilon whatever distance h whatever, right? So it's the square root of an exponential, and this we call it the signed distance between the two given horocycles. Yeah, although the sign is of course hidden already in the exponential, the result is actually positive. And or we also call it the lambda length of the geodesic, but with respect to the two given cycles. Yeah, so that's all I'm going to say. And the point is now, if the theorem of Penner says that if you give me any four horocycles based at four different points at infinity, yeah, and then if we just number these points counterclockwise, the base points, then the six possible lambda lengths that we can calculate, because we would have 4 points, and then it's 4 choose 2, so 6. The 6 possible lambda lengths satisfy Ptolemy's equation. That's what it says. And what we did yesterday is we provided an elementary proof of this equality based on a computation that of which I left. I think that one of the formulae I presented is wrong. So I owe you a correction, and you can do it anyway because it's like just a computation of an intersection of two circles. That's where where I think the mistake in my computation was. But in any case, this this can be proved using just like a hyperbolic and Euclidean geometry. Okay, and then I stressed one fact, which was that this is true for any quadruple, any ordered quadruple of horocycles based at 4 points, and then I just you know, here for this expression, just it's important that the numbering happens in the clockwise sense. That's it. Okay.
Sorry, can you
Yeah.
ask the question? So the horocycles need to be in this sort of positive distance situation, or can they intersect?
Oh, no. Yeah. So this of course I did it so that the picture didn't look so ugly.
Okay.
But if you decide to give me this other horocycle, you know, okay, so
the theorem still
it still works. Yeah. Or if some you know some horocycle. Now I'm yeah. I don't see it right away, but some horocycle that maybe intersects just you know, two of them or whatever. Always, it doesn't have, the configuration doesn't have to be so nice. This was just so that the yeah. But so in these situations are allowed here. Yeah. Okay, and then we discussed a little bit about Teichmüller space, the Teichmüller space of the Teichmüller space of hyperbolic triangles, and then we saw that it has only one point due to the simple transitivity of the action of PSU11 on triples of points oriented anticlockwise, lying on the circle at infinity. Yeah? So, and now we also discussed the Teichmüller of hyperbolic quadrilaterals. So now, so the thing is now, what we somehow the beginning point and changing a little bit what I said yesterday is somehow the beginning point is some, let's say, quadrilateral in the Euclidean plane, and just with and then I just somehow distinguish one point, which will be kind of, which is, I think of it as the first point, the first vertex of among the four vertices. Yeah, and so if you want, this is the distinguished vertex 1, and then everything, I'm going to do everything in the counterclockwise sense. So once I have this convention and the convention that I'm going to do everything counterclockwise. So let me write it here. This automatically tells me this one has to be the second vertex, this one has to be the third vertex, and this one has to be the fourth vertex. Okay, and now also as we said yesterday, so somehow the question is the question super informally or roughly put is in how many ways can we put a hyperbolic metric on this quadrilateral in such a way that these 4 points, the four corners, become points at infinity, and also that the sides become geodesics joining them. That is like very roughly put, because in a more refined way, I'm going to say, I'm going to also put the condition that among any such realization, I can locate the first vertex. Yeah. Okay, and then we said, okay, asking that how many different hyperbolic metrics one can put there is kind of, okay, so how do I put a metric here? Right? So what we do rather is just say, we change the problem a little bit, and then we say, let's instead see in how many ways we can choose 4 different points in the circle at infinity of the hyperbolic plane with one distinguished vertex. So ordered 4 tuples, and then just with the being careful enough so that the ordered 4th tuple, when I follow it, it actually follows the counterclockwise orientation around the circle. Yeah, and then we grow to that set. You know, it's ordered tuples, P1, P2, P3, P4 in the circle at infinity. So now it's S1 to the 4th, S1 infinity to the 4th. Yeah, such that such that they are different. Yeah, so that is P1, P2, P3, P4. It has exactly 4 elements. Yeah, and counterclockwise oriented. Yeah, so kind of the picture to keep in mind, to have in mind, is that to give one such point in this set or in this space is, you know, I have to give you 4. Yeah, but it's not only give you only the 4 points, so not give you only this convex hull, but actually there is a distinguished one. So I don't know, let's say that this one is the first one, let's say. Yeah. So this automatically has to be the second one, this one has to be the third one, and this one has to be the 4th one. Okay, and then somehow the idea is that every time we fix one such quadruple, this automatically gives me the hyperbolic quadrilateral, and then we think that this is one of those hyperbolic metrics that this provides one of those hyperbolic metrics that we were looking to put here. Okay, but then we said, yes, but let's say this set up to orientation preserving isometries of the hyperbolic plane. So modulo the action of PSU11, which is for the Poincaré disk, is the incarnation, the concrete incarnation of the orientation preserving isometries of the hyperbolic plane, which acts, I just recalled, which acts on the Poincaré disk and the circle at infinity by Mobius transformations. Okay, and then we called this set, or let's say space. I mean, I can at least say, okay, it is a space, right? At least it has some topology coming from somewhere, and we called this the Teichmüller space of the square. But let me put let's say this. I mean, just to indicate that somehow having the distinguished first vertex is important. You know, to actually, you know, to actually say that, for instance, having this one as a first one, having this one as the first vertex gives me here really an object different from having this one as a first one, even though the hyperbolic quadrilaterals are actually the same. Yeah. Okay, and then we started saying, because of the simple transitivity of the action of PSU11 on order triples of points on the circle at infinity oriented counterclockwise, any point here is a PSU11 equivalent to a point, to a fourth tuple where the first vertex is I. So where this one is the first vertex, the second one is -1. The third one is -I, yeah, and then the fourth one. For the fourth one, I cannot say is whatever I want, right? I mean, here I said the first one I can set it to be modulo this one, to be whatever I want. The second one I can set it to be whatever I want modulo the action. Same thing for this, but for the fourth one I cannot set it to be whatever I want. So this means that for the fourth one I have an entire degree of freedom, you know, how to say, of dimension, of real dimension 1. So this means that actually this set is at least as a set, it is in bijection with this part of the circle. Let me just at least with this part of the circle, which is when I erase this closed subinterval, right? So here is I, and here is -I, yeah? Which, if you want, is diffeomorphic to whatever, to R or to the open interval 0, 1, etc., or even to diffeomorphic to R positive. And somehow this is the one I like, R positive. Okay. Now for more points we do the same, except that now you see. So let me maybe copy all of this. Yeah. Except that now, for example, let me do it for 5. Now, of course, here instead of a quadrilateral, I'm going to have a Euclidean pentagon. And you see, combinatorially, what matters is just the 5, and to just agree that there's going to be this is going to be ordered 5 tuples. That's it. So I don't even need it to be an Euclidean pentagon, but that's just kind of to fix ideas. Yeah, with a distinguished vertex. Yeah. Okay, and now here I put P5, and then of course this leaves here. Yeah, and again modulo the action of PSU11. So now for the same story, but now one point in this set is given by something that now looks like, so I have some fifth point here. Let's say P5. Okay, and now same story in the sense that any point here is PSU11 equivalent to a point, to a 5 tuple, where the first 3 I can set them to be whatever I want, so I set them to be what I want. But for the fourth I have freedom, and once the fourth is chosen, for the fifth I have freedom. Freedom in the sense that, not freedom, but freedom in the sense that, it can be any point here, but not freedom in the sense that I can set it to be whatever I want. That I can set it whatever I want, modulo the action of PSU11. So for the fourth one, I have the 1 degree of freedom. And once the fourth one is chosen, I always have for the fifth one also an interval as another real degree of real free parameter. Yeah? So this means that here, but of course, I mean this for the fifth one, for where to choose the fifth one from, I will always have this sort of open interval, but of course that open interval depends on which one the fourth one was. But topologically, it's just an interval. Yeah? So what I do is, rescaling appropriately, or I would have to do the exercise of normalizing, normalizing that the last interval, and now this should give me, this should give me, here, square here if you want, or I could even mix, right? I mean, here square, or I can even mix, right? Like say for one I take up an interval, and for the fifth one I take R positive, whatever. Okay, the point is that now it's a two-dimensional space. And you see, and we can see that this dimension 2 is really 5 minus 3, where the 3 comes from the simple transitivity on triples of distinct points. So in general, it's going to be so let's say this is that. So in general, do I have more? No. In general, what? We have the corresponding definition, let's say, for Pn with one distinguished vertex. All I need is the n, because the distinction really comes in the when I declare what the points in this set are. Okay. Anyway, whatever. That this is actually R to the n minus 3. And let's say we can say positive here, or whatever. So the main point is n minus 3 real parameters. Okay. Now decorated. So what I'm going to do now is simply take the points, declare a point in decorated Teichmüller space to be a point in Teichmüller space, but with one horocycle based at each of the points here. Yeah. So let me do copy paste. Yeah, so now it's going to be decorated. So here is going to be, oops, here is going, sorry, here is going to be tilde. Yeah, and now again, in the very end, I'm also going to mod out by the group of isometry, the group of orientation preserving isometries, so that won't change. But now here, the points here, instead of being just 4 points at infinity, or with ordered, what I'm going to do is to decorate with horocycles based at those points. So really, really here now is going to be, since each horocycle determines uniquely its base point, I say 4 horocycles satisfying that their base points are all different. So where pi is the base point of hi. So now, of course, this space, at least before modding out, now this space is a lot larger. Right? Now here the base points live in SU11, not in SU11, in the point at in the circle at infinity. Yeah, but these ones are horocycles. And now this space is a lot bigger than the one before, because now at each point I have one real parameter of freedom, because for instance here I can choose any horocycle, so I can choose this one, or I can choose this one, or I can choose this one, or whatever, where the extra degree of freedom comes from simply choosing the Euclidean radius of the horocycle, which is a number between 0 and 1 open, yeah, in the open interval 0, 1. So now before modding out this space, it's kind of at each point now I have a one real degree of freedom. So it's has four more dimensions, no? Yeah, and then I mod out by PSU11, and then I say, okay, so now I'm going to try to see how it looks like in simpler terms. So again, since I'm talking about ordered horocycles, so that there's a first horocycle, I can at least say, okay, for the first 3 base points, you can set them to be exactly these ones, and then for the fourth one, once you put the first 3 where you wanted, the fourth one is some point here in the interval between -I and I, with some horocycle. And that doesn't look even differentiable. But okay, yeah, that also doesn't look differentiable. So now let me write in green. So in the end, we have I'm also drawing them not intersecting, because just so that the picture doesn't become so ugly. But you see, again, given my 4 tuple, the fact that I want to send the first base point here, second base point here, and third base point here determines already the image of the 4 horocycles. So it's like I cannot also say. I cannot say, okay, first send the first one here, second here, but also send the first horocycle exactly in this one. I cannot say that because I would be breaking the uniqueness of the simple transitivity. So this means that then this space should be, well, I have 1 degree of freedom here, namely the radius, fourth, but also I had a degree of freedom here, so it's 5-dimensional. So this one is 5-dimensional, and then I'm just going to say that this is, let's say, to the 5th. the fifth. Okay, now there are okay, so to the fifth, and then if I add one more point, it's going to be, well, that degree of freedom plus this other degree of freedom, so it increases by 2, etc. Yeah? So in general, I can say that oops, this is for later. In general, I can say that the decorated Teichmüller space of the decorated Teichmüller space of Pn, it seems to be, how is 5 related to this 4? It's what is it? It's I think it's 2n minus 3. Yeah? So it's going to be 2n minus 3. It's not, yeah, it's not isomorphic to n minus 3, to r, let's say, positive 2n minus 3. Okay. Now, this parametrization, this parametrization of this decorated Teichmüller space has one problem, which is, or like one not so nice feature, which is that the parameters, they don't have all the same nature. For the here, for instance, for where this point is located, one chooses a point in this interval. So that's the kind of the nature of one parameter. But the nature of the other parameters is slightly different. Is to fix the radius of something. So I mean, I know that you are going to say, yeah, but it's still an open interval. Yeah, but you see, kind of, at least in a way, like kind of philosophically, looks a bit different. That I'm really fixing something that combinatorially doesn't look like the other parameter. And that's one really nice feature of lambda lengths, that they uniformize this, because you see here I already have my I have my horocycles. It's almost looking like Ptolemy's configuration already. If you give me a point here, it looks almost like a Ptolemy configuration. And now the thing is consider again this quadrilateral. If you give me one triangulation, to give one triangulation, you need to give me to tell me, okay, take this diagonal or take the other. Right? And for that, to tell me that in terms of the special point, you only need to say take the diagonal that contains the special point, or take the diagonal that doesn't contain the special point. And once you decide, let's say that we take this diagonal. Let's say that we take this one. So is it visible? Let's say. Then every time you give me a 4 tuple, since I know which one the first one is, I automatically know. I can automatically determine triangulation by ideal triangles. Namely, well, of course, I have the 4 sides. But then, okay, the last one, that doesn't look like very geodesic. But yeah. I mean, they are supposed to be orthogonal to the boundary circle. Okay, yeah, but the fact that there is a first one is telling me, it doesn't matter which point you give me, the combinatorial triangulation induces automatically a triangulation by geodesics. And given the triangulation by geodesics, I can measure the lambda lengths, which, how many there are? 1, 2, 3, 4, 5. There are 5 lambda lengths. Okay? So we take those lambda lengths, and what Penner proves is that it doesn't matter what triangulation you take. This assignment of, you pick a combinatorial triangulation, and then with that triangulation, for any point in the decorated Teichmüller space, you induce a triangulation by geodesics, and then you take the lambda lengths of the horocycle, of the geodesics with respect to the horocycles, and this gives a parametrization of decorated Teichmüller space. So in this case, for instance, the 5 lambda lengths give a full parametrization of the decorated Teichmüller space. So this is nice. Where of course the lambda lengths are exponentials of whatever, so they are positive real numbers. And the nice thing is that here all the 2n minus 3 numbers, now have the same nature. Okay. Now, why did I leave this space? I don't remember. Why did I leave that space? Yes. Because flips induce change of coordinates. Because you see now, of course, it's okay. But what if I had chosen the other one, the other triangulation? So let me maybe copy this, which is legal, right? I mean, one could have said like, don't take that one. Don't take this combinatorial triangulation. Take the other one. So let me do copy paste. Take the other one. Then, given any triangulation here, not any triangulation, given any point in the decorated Teichmüller space, now the other triangulation induces again triangulation by geodesics. This one also gives a parametrization of the decorated Teichmüller space by r to the 5th positive. And then what is the change of coordinates? The change of coordinates is provided by Penner's theorem, by the other theorem of Penner. Let's see, by this one. Oops. Okay, I don't know what happened. Anyway, I mean, maybe I will just keep going. Because you see that the thing is that now lambda 1 3 you see, as functions defined on the decorated Teichmüller space, I have the equality lambda 1 3 is equal to lambda 1 4. Lambda 1 4 times lambda 2 3 plus lambda 1 2 times lambda 3 4 divided by lambda. It was the other way around. Sorry, it was the other way around, because this is a new triangulation. So it's lambda 2 4 and then divided by lambda 1 3. And the other 4 coordinates remain the same. So Penner's theorem, what it really gives me is the relation between the coordinatization of the Corioto-Teichmüller space provided by this triangulation and the coordinatization provided by this other triangulation. And this is actually, and Ptolemy's, and Penner's theorem is actually kind of an equation between functions defined on the Corioto-Teichmüller space. Okay, so that's one thing. And now, of course, something I would like is, you see, now I'm talking about a pentagon. And I know that the triangulation you are seeing there gives a parametrization of the Corioto-Teichmüller space of the pentagon. And I know that this diagonal also induces a lambda length coordinate. Right? I mean, it induces a lambda length function because whatever point in the Corioto-Teichmüller space of pentagons, which means 5 horocycles, to whatever point there, yeah, with a distinguished first point, let's say this one. For that one, gamma also induces a lambda length. No, I mean there you are seeing in blue one point in the Corioto-Teichmüller space, yeah, and then gamma induces, let me see, this geodesic. And hence there is the lambda length with respect to gamma, which would be the lambda length of this segment, yeah? Which is not the hyperbolic length again. Okay, so I can perfectly do that, and then somehow now I have a question, which is, yeah, so could it be, can I express the lambda length corresponding to gamma as a function in terms entirely of the lambda lengths of this other one, maybe as a rational function, or let's say in principle as a to have some expression here, so that the equality is valid, let's say, in some open dense subset of the Corioto-Teichmüller space, let's say. With that would be already a satisfactory answer. If it holds on all the Corioto-Teichmüller space, better. Yeah. And then somehow here I give you that question. So what do you think, and what will be the strategy that you would follow to solve this question? Right, doing 2 flips because yes. Okay. Using exactly, no, and then I use the sequence of 2 changes of coordinates. Right? So actually, yeah. So that's what Sergio is suggesting. It's exactly what you are suggesting, right? Did you see it? I know you couldn't see it. I guess you could have seen it. No, wait. Yeah, no, you couldn't have seen it because this I did. Yeah, this is not there. This is not there. Yeah. Okay. Yeah. All right. And now I make those substitutions, right? Then here I'm going to say in the first substitution, what lambda 3 is going to appear in the denominator. Yeah? In the numerator, there's going to be this lambda. Let me think. Sorry, not the other way around. So once it's here, I express lambda gamma in terms of these 4. You see it? I mean, Sergio said, okay, perform this sequence of flips to put gamma inside the triangulation. But now, once I'm here, I say, okay, lambda gamma can be written in terms of these ones. right? This one is 2. So when I write lambda gamma in terms of these ones here, lambda 2 is going to appear in the denominator. Yeah, and yeah, okay, fine. And yeah, and then I have to express this one in terms of these 4 here. So you see, and when I express this one, which appears in the denominator, which appears in the numerator for lambda gamma, lambda 3 is going to appear in the denominator. So the denominator of lambda the denominator lambda 2 doesn't interfere with the denominator lambda 3, and in the end, in the expansion, I should expect in the denominator lambda 2 and lambda 3 to appear. But somehow in these first 2 substitutions, there's going to be no obstruction for seeing that actually what I have in the denominator is just a Laurent monomial. Yeah, and then here is the result of those substitutions, and you see the lambda 2 and lambda 3 somehow we know why they appear there. Yeah. But then you see the thing is when one starts playing this game and one has like some larger polygon, it is when one performs one more flip, like for instance, now lambda gamma is this, and now if I perform some flip where lambda gamma appears, now all of this is going to go to the denominator. And then a priori there's going to be like a kind of a priori very ugly rational functions that start appearing in the numerator and in the denominator. And later we will see that actually, and this is a beautiful theorem of Fomin and Cholewinski, this is never the case. So it is always true that when one performs the substitutions and simplifies, the denominator is always a Laurent monomial, which here, for instance, means that this equality is valid in the whole of the decorated Teichmüller space, not only in a dense open subset. I mean, this kind of equality between functions defined on the decorated Teichmüller space. Where do they live? They live inside the ring of all real valued functions defined on decorated Teichmüller space. That's where they live. Okay. And now I don't know if I have 41 minutes. The point, and this is probably what makes actually what I've said so far actually interesting, is that the story can be adapted to treat surfaces with marked points. But there has to be a slight change of perspective, because of the following. So somehow our opening question, our starting question was the following. I give you a polygon, let's say with one distinguished vertex. And then somehow the question is, in how many ways or how many different hyperbolic metrics can I put on the polygon in such a way that the vertices become points at infinity, the sides become geodesics. And then as such, the question is not easy to answer, so we change it slightly to say, okay, now just consider polygons that are already inscribed in the circle at infinity. Okay, now we have to make the corresponding questions for surfaces. So it would be, in how many ways can you put a hyperbolic metric on a surface of genus G with endpoints removed in such a way that, let's say, those points become points at infinity, let's leave it like that. So that's the question. As such, it is very hard to answer. So one goes to one turns to, okay, let's ask something more tractable, like just taking points on the circle at infinity. The problem is that now what you have is a surface, not just a polygon, right? So how do you do that? And the answer is fortunately given in terms of Fuchsian groups. Fuchsian group. So let me list this maybe let's say very quickly. So definition: a Fuchsian group is a discrete subgroup of, let's say, PSL2R. Although what we really have in mind is the isometries that preserve the orientation of the hyperbolic plane. And here you can put Riemannian, Riemannian or metric isometries, whatever you want. Okay, and this is a funny definition because, okay, I mean, for that type of group, you already have a terminology, right? And this discrete subgroup of something. Why do you give another name? You already have a name, right? But okay, that's a Fuchsian group. And there are some very nice theorems. One is that let's say, so here comes some technicality that somehow that one realizes once one has already studied a little bit of Fuchsian groups, which is something that that from your surface you are removing points, and those points, when you put metrics, those points, bless you, those points, when you put metrics on the surface with those points removed, the metric on the surface may not be able to see, at least a priori, whether that you really have a point, or if it's like if it becomes a circle at infinity, for example. Right? Okay, so one starts speaking about Fuchsian groups of certain specific types. Yeah, so that makes that ensure you that those points really become one, that each point removed really becomes one point at infinity. That condition, like for instance, if you go to Penner's book, it means that peripheral elements of the fundamental group go to parabolics. But I don't want to go too much into that. Just that it is possible to impose that condition for the Fuchsian group to guarantee that the quotient of the hyperbolic plane modulo the group has the property that that point is one point at infinity and not a whole circle at infinity, a funnel. Okay, there are then two nice things, which are the following. One is the uniformization theorem that somehow was already mentioned in Professor Tomasi's course. Which says that for every hyperbolic metric or structure on let's say your surface, let's say that the surface is sigma, and then we remove the points, let's say Pn. There is a Fuchsian group. A Fuchsian group, let's say torsion free. That's like a condition that guarantees that there are no orbifold points. But anyway, so a torsion free Fuchsian group gamma, such that there is such that, let's say, one has the hyperbolic plane. One has the projection to H modulo gamma. This is the projection, and so that here there is a biholomorphism to sigma minus, not biholomorphism, an isometry. Oh, I mean also a biholomorphism, but an isometry between this hyperbolic surface and your sigma minus P1 Pn with the hyperbolic metric you imposed. Yes, and in such a way that these ones become each one a single point at infinity. Yeah, but this I'm not stating. Yeah, if you want isometry and actually biholomorphism. Yeah, maybe. I mean, I'm of course not stopping to say what conditions one needs on the number of points. Yeah, or like you know, when sigma has genus 0 and so on. But these are conditions that Professor Tomasi has mentioned. So that's one theorem, and then the other theorem is that if you have two Fuchsian groups, gamma 1 and gamma 2, that's another theorem. So if gamma 1 and gamma 2 are Fuchsian groups, then H modulo gamma 1 is isometric to H modulo gamma 2. Of course, we would like to know when this happens. And this happens if and only if gamma 1 and gamma 2 are conjugate subgroups. Are conjugate subgroups. Or subgroups of where? I mean, of where I know they are subgroups. So, and there's one more theorem, which is that if you have at least one puncture, if you have at least one point that you are removing, then how do you recover gamma from the actual surface? This is really a really beautiful theorem, I would say. So if you have, one more theorem. If you have gamma a torsion-free Fuchsian group, the fundamental group of sigma of H modulo gamma based at some point, right? You have to base it at some point. You base it at whatever point. Then this one is isomorphic to the Fuchsian group itself. So this is how you recover the group from if you give me the surface. Okay, and then these theorems somehow give the hint on how one can define the Teichmüller space, you know, for G, comma N, for that information, and then one defines it as the, you know, the set of all injective group homomorphisms, let's say phi, from P pi 1 of sigma, your combinatorial surface on which you are imposing a hyperbolic metrics, minus the points, based at some point, right? Based at some point in sigma minus P1 to Pn. From this fundamental group to PSL2R, yeah, with the properties that phi is injective, so that you indeed recover. I mean, there are no collapses. Phi is injective with discrete image, so that the image is a Fuchsian group, isomorphic to pi 1. Yeah? So if is injective with discrete image, yeah, and sending peripheral elements to parabolic Möbius transformations. Okay. I mean, I would say that from this theorem, somehow it's clear like why one considers this, because this is one way in which you can start rescuing the Fuchsian groups that will give you hyperbolic metrics on sigma minus and then minus the points. And then what is a peripheral element? You see, let's say that on sigma you have the point pi, which gets removed. Yeah, and then your base point star is somewhere in the surface, and I'm assuming the surface connected, of course. And then from the base point you can go to pi by in many ways, right? In many ways. Take any such, yeah? and now that one, for that one, consider the following loop, the loop that kind of surrounds it very closely. We call that a peripheral element. So for each trajectory from the base point to pi, you have a peripheral element, and then in this set you consider those that send peripheral elements to parabolic Möbius transformations, and that's the condition that ensures that this point will become one point at infinity, yeah? And not a funnel. Okay, and now this.
So you choose a parabolic transformation because those are the ones with more than 6 points.
Right. Yeah, and then exactly, and then this point somehow morally, what happens is that this point becomes the fixed point of that parabolic, and becomes in the projection becomes a point at infinity.
Something I don't understand is these peripheral elements. They're supposed to be loops that are very close to some trajectory to pi, but aren't they all monotopic?
Not all of them, right? Because for instance, consider the torus. Like you can go directly, or you can go directly, but you can do this, surround, and come back all the way in the same way. Yeah. And actually, if you have one peripheral and any other trajectory, somehow, you have any peripheral and any element of the fundamental group, the conjugation gives you another peripheral. So you actually have many. Yeah. Okay, but that is the set, right? That this is somehow what corresponds to considering just ordered tuples of points in the circle at infinity. We still have to mod out by isometries and blah blah. But you see, here if you take any such representation of the fundamental group, well, and you take any element of PSL2R, you can conjugate the whole representation, but that element. You conjugate simultaneously the whole representation by an element of PSL2R. So PSL2R acts on this set by conjugation. Yeah, and then this is another way to define, like different from the one we saw in Professor Tomasi's course, the Teichmüller space of, let's say, just Gn. Okay, and then one decorates it with horocycles, and then there are several papers where they show, like, culminating in a really nice paper by Fomin and Thurston, that culminate in the result that everything we said about polygons is also true for the decorated Teichmüller space, the decorated version of this. Okay, so that's about it. I don't want to go more into this. So let's switch to the Farey diagram. Yeah. Okay. So I'm going to begin with the primary school dream, which was to define the addition this way. So of course, we know that this is not possible, right? I mean, at least not in the naive way we would like. We would need a little bit more. So what we are going to do is we are going to define an addition this way, but to make it well defined, we do it over the reduced expressions of fractions. So a fraction, a rational number written as a fraction, we say that the fraction is reduced if two things happen. First, the denominator is positive, and second, the numerator and the denominator are coprime. So you see, these two facts make the reduced expression for each rational number unique, where, for instance, 0 is 0 divided by 1. Yeah, and I'm actually going to say it's useful to say that, for example, infinity is 1 divided by 0. So let's say greater or equal, so that infinity has its reduced it has one fraction, and then for infinity the uniqueness is broken, because infinity is also minus 1 divided by 0, and the denominator is again non-negative. And this is a bit annoying sometimes, the fact that it's not unique, but it's useful to keep this in mind, that those possibilities in mind. Yeah, and then we define the naive addition, the naive sum of two rational numbers, or even with infinity. With infinity, but then we have to take, there are two possible. But at least for rational numbers, we do it the obvious way. And now this is well defined, because we are doing it for R and S in terms of the reduced expressions, which are well defined. So the naive addition is well defined if we do it this way. Okay. So some examples like you know, like kind of to compare the naive addition with the actual addition. They are clearly not this. I mean, they are not the same. And then we have actually an easy observation. Like for instance, the usual addition of two positive numbers is to the right of both of them. But then if you take the naive addition, it's actually in between, and it's like incredibly. I wrote es decir. Sorry. Yeah. So would it be correct if I say this? Sure. No, with O. Like this, no? Yeah. Okay. Okay. And now we use this naive addition to construct the Farey diagram, and we define it recursively as the limit of a sequence of graphs. So the Farey diagram is going to be a graph. The zeroth graph, the starting point, is the graph that has the integers and infinity as vertices, and its edges connect consecutive integers and each integer with infinity. Yeah? So this graph V0 looks like those are the integers. I don't know. Let's say 0, 1, 2, 3, etc. -1, -2, and then there are the edges that I write like this, kind of just not to confuse, not to think that I'm taking the interval, and there are all the edges connected to infinity. Yeah, so that's the starting point. And now the recursive step is that once at level n the end graph has defined, or the end level of the Farey diagram has been defined, we introduce all the naive additions as vertices. We introduce besides the vertices we already had, we introduce the naive additions, or the naive sums between points that are already connected by an edge. So in other words, all the vertices that were already constructed, they go in, but also for every edge I take the mediant, the naive addition, and I put it as vertex as well. So, and I do this for each edge. Yeah. Okay. Yes. Yeah. And then what else? So that's at the level of vertices. That's for the vertices. Now for the edges, I take the edges I already had. I don't discard the old edges, and I add new edges as follows. Like every time I had an edge in Vn, so this in Vn. Now for Vn plus 1, I'm adding a new vertex, which is the naive sum, and I add these two new edges. So the edges connecting the old vertices of the edge to the new vertex added to the configuration. And then the Farey diagram is just the limit of these graphs. So the vertices are all the vertices that I obtained along the way, all the rational numbers that I obtained along the way, and all the edges that I drew along the way. So some you know, like some steps. So for example, here, if we start with 0 and 1, then of course there is they are both connected to infinity. But then, you know, from this edge, which is at level 0, at level 1, I have to introduce their naive addition, their naive sum, which is of course 1, you know, 1 divided by 2, of course, and I connect them to the new one. So that's why. Yeah, so let me, yeah, okay, so I'm just going to leave it like that. And then that's in passing from level 0 to level 1. Now at level 1, I already have this. And then what I do is I take a naive sum of this, yeah, and introduce also the edges. Naive sum of these two, and introduce the edges. Yeah, so this is what I have at level 2. At level 3, the same. For this one, introduce this one. For this one, introduce this one. For this one, introduce this one. For this one, introduce this one, etc. Yeah? So that's how the recursion works.
How important is this naive addition? Could you just, I mean, from the point of view of the graph, could you just divide each segment into parts, sort of X?
I mean, the thing is, for example,
I see some show up at a much further level, so 1/4, 1/3 shows up
right, and
further away. Yes.
and then you see, I would say that for instance, 0, 1 is never going to be connected to 2 divided by 7.
Right.
I would say. Yeah.
Sorry.
Okay, and of course, you see, like now what I'm going to do is, I mean, this way of drawing, I mean, it is having the numbers all scattered this way is not nice. So so we prefer to have rather all the numbers on the real line, and we better draw the edges curved, right? And we already have a gadget to do that. So that's what we do. So we do it. You know, we draw the edges of the Faraday diagram as actual geodesics connecting the two endpoints. So for instance, here you have 0 and 1/2, and then this is the naive sum, which is obviously 1/3. Okay, so that we do that. And then I guess this is what maybe you want. I guess a one-shot way of saying when two things are adjacent or not. So first of all, I mean, we started with the integers and infinity, and together with the naive sum, we started creating other rational numbers. And I would say that a priori is not, like, at least not on the nose obvious that one obtains actually all rational numbers along the way. So which rational numbers actually occur? And second, if you give me two things, two points that we know for some reason that are vertices of the Faraday diagram, to decide in an easy way whether they are connected or adjacent or not. And the answer is, I would say, quite beautiful. Is if you give me two different vertices, written already as reduced fractions, they happen to be adjacent in the Faraday diagram precisely when the determinant of them seen as a matrix is plus or minus 1. So, I mean, you see here there's a rational number, so, and then, you know, A divided by B seen as a matrix, seen as a vector, CD seen as a vector. Determinant of this is precisely this. I mean, if you think about it, it's kind of, this is somehow the way we obtained the formula for Mobius transformations, right? Because we divided by the second entry, and this is somehow, that's exactly somehow what is going on behind the curtains for this. So let me see the proof. I like the proofs. So yeah, I have 9 minutes. See, yeah. So let me go over the proof. 1 second. 1 second. I mean, sorry, I'm somehow hesitating about this queue. Yeah, no, it's fine. It's fine. So we're going to show by induction on n. So it's like by induction on the level of depth in the Faraday diagram. That for any two rational numbers, it so happens that that they are connected there, if and only if this happens. So there, I think I'm already making some assertion. Yeah, I mean, as a corollary, I'm going to obtain that one really hits all rational numbers in the recursive procedure. Anyway, so in the inductive basis, one is talking about E0. So if you give me any two rational numbers and they are connected in E0, well, what happens is that those two rational numbers must be integers, or one of them infinity, and they have to be either consecutive integers or integer and infinity. So, but the expression, so the possibilities are m and m plus 1, or m and infinity, or m plus 1 and infinity. So now I take the reduced expressions, and then I just check the determinants, right? Like, for instance, this determinant is obviously minus 1. This determinant is also obviously plus or minus 1, etc. So every time I took two rational numbers, and if they and they happened to be adjacent in E0, this was true. Okay, and for the inductive step, for the inductive step, what do? Is inductive step to show this, right? So we assume star for n, and we want to prove it for en plus 1. But so you see, the thing is, for en plus 1, my two rational numbers are connected if and only are adjacent, if and only if either they were adjacent already in En, or they come from or they were not adjacent, which means that they have to be their adjacency comes from one of them being the naive addition of two things that were adjacent before. So that's what I express. So you see, one of the numbers then has to be the naive addition of two things that were already there. Yeah. Okay, and then I just take the determinant of this against this one and of this against this one, and I just check that it can be entirely written in terms of the previous determinants, and it's plus or minus 1. So this finishes. I mean that's the inductive step that finishes one side, and then the other side is nicer. I mean this is more or less, I would say, routine, but the other way is very nice, I would say. The thing is on the, we are kind of on the way back. Now we are on the way back, but on the way in, what we did is actually every adjacency, every edge of the Farey diagram, we labeled it with a matrix of which we took the determinant. So in other words, this edge was labeled with well, I mean, with it depends, because you can say, okay, I label it with the matrix A, B, C, D. If I'm writing R before S, but if I'm writing S before R, it's not that one. It's C, D, A, B. Okay, so how can I make a choice? Well, just write S on the right whenever it's bigger. In which case, then just to have positive determinant, we actually labeled with the writing S first and then the smaller in the second column. Yeah, so somehow the picture becomes that in the inductive step we have here we had AB, CD, and this was the given adjacency. So somehow this is this, and then we label this with C, D, A, B. Yeah, and then the new adjacency in the inductive step is the naive sum, which is a point somewhere in between with the new two edges. So this is A plus C. B plus D. Of course, when I write this, I'm already assuming that this is reduced and this is reduced. And then here the labeling would be A plus C divided by B plus D, and AB. Sorry, not divided. B plus D, and then A, B. That's the labeling of that edge, and the labeling of the other edge would be C, D, A plus C, B plus D. And that's the labeling of the new edges. Okay. Okay, so now let's take vertices. Let's take vertices of gamma, yeah, and then such that the corresponding determinant is plus or minus 1. And what I want to show is that they are connected in the Farey diagram. Right? I mean, here I just told you on the way in, this is what we did. This labeling. And now I'm going to show you that if the determinant is 1, then they are connected by an edge. Okay, now, of course, I can assume without loss of generality that at the level of denominators, beta is smaller or equal than delta. That this I can assume without loss of generality. Yeah. And now I allowed beta to be 0 because I said I'm also considering infinity as a vertex. Right? Okay, but then if beta is 0, then delta has to be greater than 0 because the determinant is plus or minus 1. Right? So it cannot be that beta and delta are simultaneously 0. because the determinant is plus or minus 1. Okay, but so you see, if beta is 0, in this alpha del, okay, tempus caducto.